In the previous videos for this section, we looked at consequences of our original function based on behavior of the derivative. So we saw, just to summarize, that the critical points of our graph occur when the derivative is 0 or undefined. And those critical points are critical because they often tell us where the maximum or minimums of our graph occurs. Similarly, we can find information about how our graph increases or decreases based on the derivative. So I'm just going to bring up a graph that we saw in the previous videos here. I'm going to erase some stuff here. But what we found in the previous videos was that our graph had a local minimum at -1 and a local max at +1. So what happens between these two critical values, these two local min and max? Well, between these 2 points, our graph increases the entire time. So what would we expect about our derivative always everywhere on that interval? Is our derivative going to be positive or negative? Do we know? Well, it turns out when our graph is increasing like this, that means our derivative is going to be positive. We're always gaining more output for every input we move. And derivative is exactly that rate of change of vertical or change of horizontal. So whenever we're increasing, our derivative is going to be positive. So then between these two intervals, we have that our derivative, if we call this function f prime of x, is bigger than 0. So the derivative doesn't necessarily increase. In fact, it increases here and then starts to decrease because our rate of change slows down. We get less steep. But we at least know that those slopes of the tangent lines are positive. Now, what about over here on the left side? What's happening to our graph? Well, these derivatives, there's tangent lines rather, they all slope down when we decrease. So f prime of x is less than 0 on this interval here. And then similarly on the right side, as we decrease, we can draw in those tangent lines. See their slopes are negative. So our derivative function would be less than 0. So that's exactly what this first derivative test tells us. So before I write the test, I'm first going to just summarize what we just wrote down or what I just described on the previous graphs. So that is, if the derivative f prime of x is bigger than 0, so that means those tangent lines have a positive slope, that means our original function f of x is increasing. If our derivative f prime of x is less than 0, that means our original function f of x is decreasing. And rather than memorize these two statements, I really encourage you to try to conceptually understand why this is happening. So for myself, I always just like to draw a little visual, maybe like a little squiggle graph here, and then consider those tangent lines that are on our graph at various spots. So if I know what an increasing function looks like, it looks anything like this. I can ask, what are those slopes of the tangent lines on those kind of graphs? Okay, they all look positive. And similar for a decreasing graph or a decreasing function. Okay, so from these two statements, these two facts, we get our first derivative test. So let's write that out. So what that first derivative test actually tells us is about our local maximum and minimums on our graph. So just getting set up here, it says the following. So if we're considering, let me just go back to that graph that we were looking at here. We knew based on looking at a graph that this value here at +1 was a local maximum. So what's happening with the derivative on that maximum? Well, on the left, our function is increasing. On the right, our function decreases. So our derivative goes from positive on the left to negative on the right. So that's exactly what that first derivative test says. It says if your derivative goes from positive to negative, then that in-between point where you have a 0 must be a local maximum of your function. So let's summarize that. So I could say if f prime changes from positive to negative, then our function f has a local maximum. I'm going to write more space here, or use more space, local maximum. So again, I encourage you to draw pictures rather than memorizing. So I like to draw a picture. Okay, change a sign from positive, so that means we're increasing, to decreasing. We move along the graph like this, and that means, get my highlighter out here, that on the left, my derivative must have been positive, so f prime of x is bigger than 0. On the right, we're decreasing, so f prime of x is less than 0. And so at that point where the derivative changes sign, we must have a max. And it's going to be a local max because we don't know what else happens to our curve as we continue moving. All right, so what do you think might be the statement or the situation if our graph, or derivative rather, goes from negative to positive? We get a local minimum. Exactly right. So it's the first part of the statement. The second part says if f prime changes from negative to positive, then f has a local minimum at that in-between point. So you can draw a little cartoon for yourself. So if our derivative is negative, we're decreasing, then positive, so we're increasing. So that in-between point is our local min. All right, so now let's put this first derivative test into practice by looking at our first example on this page. So number 6. Number 6 says use that first derivative test to find the location of all local extrema for f of x equals x cubed minus 3x squared minus 9x minus 1. I'm going to use a graphing utility to confirm your results. So one thing that I just want to emphasize here from that first derivative test is the first derivative test tells us where we have local minimum and maximum values. So if you notice, the derivative test itself describes where f prime rather, changes sign, positive sign to negative sign. So in between f prime being less than 0 to bigger than 0 or vice versa, f prime must equal 0. So that's where we see those critical points come into play again. So in order to determine those local extrema, we need to find again those critical points. So let's do that. So step number 1, find the critical points. So to do that, I'll write that out here, find critical points. So to do that, as maybe a sub-step, we need to compute the derivative f prime of x. So please pause the video and compute that derivative on your own, and then we'll check answers. All right, so for us, f prime of x is going to equal derivative of x cubed is 3x squared, then minus 3 times 2x minus 9. So that becomes 3x squared minus 6x minus 9. So is our derivative ever undefined? Nope, we just have a nice looking polynomial here. So then step 2, maybe in finding those critical points, is, well, we need to set our derivative f prime equal to 0. So to solve for x right away, we can see if we divide both sides by 3, then that becomes 0 is equal to x squared minus 2x minus 9. So from there, we can try to factor. I'll bring that over here. So if I want to factor x squared minus 2x minus 9, well, I need to look for factors of 9, rather factors of negative 9 that add together to get me negative 2. So factors of 9. Good catch, everyone. We don't have a 9 here. Oops, too big of a 0. When I divide by 3, what happens to each term? So here, 3's cancel. Here, divide by 3, I get a 2. Divide by 3, I get a 3. So rather to factor this quadratic, we want to find factors of negative 3 that add to give me negative 2. So what might those be? Well, negative 3 times 1 gives me negative 3. Negative 3 plus 1 is negative 2. So this becomes 0 is equal to x minus 3, x plus 1. And so feel free to confirm that on your own. But from there, then, this tells us that in order to get a 0 here, one of these terms need to be 0. So either x needs to equal 3 or x is equal to negative 1. So now we have our critical points are x equals 3 and x equals negative 1. So then the next step here is to determine what is happening with f prime on the intervals where we look at 3 and negative 1 as being those critical points where the sign changes of our derivative. So that's maybe here number 3. So this is often called a sign chart, but what we do is we set up that number line and we mark our critical values, negative 1, 3. So we know at these points that I have here, let's highlight them at negative 1 and 3, our derivative is 0. But what happens in between? So what happens over here when x is less than negative 1? What happens with our derivative? Well, let's just test a value. So pick any number less than negative 1 and plug it into our derivative. So we could use, say, negative 2. So if we plug in negative 2, f prime of negative 2, we get 3 times negative 2 squared minus 6 times negative 2 minus 9. So there we get 3 times 4 minus 6 times negative 2 gives me a plus 12 minus 9. So I get 12 plus 12 minus 9. So minus 9 is negative. So our derivative is negative there. Good catch. So I'm glad you were watching carefully. See, I made a little typo here. 12 plus 12, not 12 minus 12. So we actually get 24 minus 9, which is positive 15. So here, when x is less than negative 1, our derivative is actually positive. And again, always on this interval, our derivative will be positive because the derivative never changes sign again because we don't have a case where the derivative is 0. We found those only 2 points where the derivative is 0. So I'm going to clean this up a little bit because I want us to check the next 2 intervals. So in our next interval, we want to determine what is f prime doing. So I'll pick a number in our interval. 0 is often the easiest number I like to use. So when we plug in 0 here, f of 0, f prime of 0 is 3 times 0 squared minus 6 times 0 minus 9. So now we get minus 9. So our derivative is negative. Then we can check that final interval. So we plug in any number here, maybe 10. F prime of 10 gives me 3 times 10 squared minus 6 times 10 minus 9. So that becomes 3 times 10 squared. That's like 300 minus 60 minus 9. So we see we don't need to even compute it all to recognize 300 is really big, 69 are not as big. So when we subtract those, we're going to still get a positive number. So our derivative is positive here. Okay, so why did we just do that sign chart? Why did we just do all this work? Well, now we can tell what is happening with the derivative of f. So what is happening and why do we care? Well, here on the start of the interval, we go from f prime goes from positive to negative. So what does that look like? Well, on that interval, our tangent lines slope upward. Then on the next interval, our tangent lines slope downward. So we see that what we have here at -1 must be a local maximum. Then similarly, as we continue, this next interval, our tangent lines have a positive slope. So we must have a local min at 3. So then to summarize, because our derivatives go from positive to negative at -1, we know that at x equals -1, f of x has a local max. And because the derivative goes from negative to positive at 3, at x equals 3, f of x has a local min. Awesome. So we found these two local extrema. So why don't we graph the function to confirm that we found the correct extrema values? So I'm going to graph my original function to find its local maximum and minimums. All right, so let's take a look at our graph now. Need to kind of adjust it here so we can see the whole thing. Beautiful, look at that. All right, so what's happening here? So where do we see our minimum and local minimum and maximum? Well, up at the top here, we see at -1, 4, we see we have a little bit of a maximum in that area, local maximum. And down here at 3, -28, we have a local minimum. Is that what we found from our previous work? Go ahead and flip back and check. Awesome, it is what we found. And just to summarize, over here on the left side of -1, our tangent values are positive because the slopes of the tangent lines are positive. Our tangent lines increase. Here in between, our tangent lines all have a negative slope. And then as we increase on the right, all of our tangent lines have a positive slope. All right, great work, everyone. Thanks for watching.